I'll admit everybody now. Oops. Welcome to this third edition of the Ambassador Waters Expert Program at U.S. Embassy Tashkent with our collaborators from the U.S. Department of Interior, the Environmental Protection Agency, and the U.S. Geological Survey. If you have not already done so, please go to the bottom of your screen and select the icon at the bottom of your screen in either Russian, Uzbek, or English, the language you prefer to listen in. Interpreters, could you please put that into the chat box for people so that they're aware that they can select interpretation? If you could just type that into the chat box. And then I believe we will start with, is it Neil or Amy we're going to start with today? I'll let them introduce themselves.
Amy will be kicking things off.
Okay.
Hello, everyone. Good morning. My name is Amy Maybach. I'd like to thank you all for attending this event here. Let me just start by saying a few words about myself. I'm a scientist with the United States government, and I've been with the US government for about 18 years. And during all that time, I have spent my career working on protecting our valuable surface water resources. So today I'm going to talk about water resiliency. And the United States is quite similar to Uzbekistan with water supply shortages. The saying goes in the United States that in any one time, we are in a drought condition somewhere in the United States. Our population has again doubled in the past 50 years. So water is in very high demand and short supply. So let me go ahead and share my screen. Can you see my screen?
We can.
Okay, thank you. All right. So as I just mentioned, our communities are constantly facing challenges related to water supply. Both rural and urban areas face unique challenges related to water pollution, drought conditions, causing water scarcity, and high runoff when it does rain. And in urban areas, development often increases impervious areas such as concrete, asphalt, pavement that does not allow for groundwater infiltration or recharge. This slide shows the health of a water body or waterway is directly correlated to the imperviousness within that watershed. Simply meaning the more asphalt, concrete, and other hard surfaces that do not allow for groundwater infiltration or slowing down of the water as it runs off these hard surfaces, the quality of the watershed decreases and water bodies can become severely impaired. So this is all this slide shows, and I apologize that it did not translate outside of English. So the traditional approach for managing rainwater has been to convey the water as quickly from the site or development to water bodies like rivers as quickly as possible. This picture here on the screen shows one such river that has severe degradation. You can see the stream bank erosion where the tree roots are exposed. Massive erosion has occurred in this area due to upstream development, housing, buildings, streets, parking lots, with large areas of imperviousness, that's concrete and asphalt. And so when it rains, water rushes off of these areas uncontrolled to nearby rivers and lakes, discharging pollution from the urbanized area. And the flows cause this bank erosion, widening of the river channel, and changes to the stream geomorphology. So the new approach to kind of address these types of problems is more nature-based solutions, like low impact development, such as green infrastructure. It's a paradigm shift to look at water more as a vital, valuable resource. Green infrastructure manages, infiltrates, evapotranspires, retains that water on site, so very little, if any, runs off site. And this allows for a greater reduction of pollutant loads to rivers and lakes, and it also creates multifunctional infrastructure. And I'll discuss a little bit more on that a little bit later. So green infrastructure, what is it? It uses systems and practices that mimic natural processes to infiltrate, evapotranspire, or reuse the water. It can be used at a wide range of landscaping scales and can be used in place of or in addition to more traditional water infrastructure, like gray infrastructure, which refers to more typical concrete infrastructure, pipes and culverts. This photo in the slide is a river in the United States, which used to be the site of a local airport at my hometown. This river was formerly in a concrete pipe under the airport runway and taxiways. So green infrastructure is part of low impact development, which is a comprehensive land planning design approach for maintaining and enhancing the pre-development hydrologic regime. It can sustain or restore a watershed's hydrologic and ecological functions, and it's a sustainable water practice. It can be applied both to new development, redevelopment, or retrofit to existing development. So green infrastructure will have a bigger impact when it is holistically integrated within the other infrastructure. So multi-benefit infrastructure is more cost-effective. Multi-benefit infrastructure can provide recreation space, increase vegetation and tree cover, and other benefits to the community. So for example, where I live, fruit trees have been planted and they're able to be enjoyed by the local residents as they produce fruit. So the photo shown here looks like a traditional parking lot. Nothing special, it looks like. But rather than traditional pavement, it has permeable pavers, which are over here by the car. And those permeable pavers allow water to soak into the ground underneath them. That is unique. Most pavers do not do that. They don't have that permeability. And so I apologize that this slide also did not translate from English. But one of the ways that green infrastructure builds water resiliency is by reducing the dependency on imported or pumped water, which also obviously reduce costs. And so, as I mentioned before, green infrastructure mimics the natural hydrologic cycle that is to take water, slow it down, spread it out, and soak it into the ground. And green infrastructure can be used or integrated into parks and open space, urban forestry, a lot of parking lot landscaping, and also as climate adaptation strategies. The bottom photo here shows the traditional parking lot with these curb cutouts right here. And that directs the water to these planted plants and trees in the middle of the area between the parked cars. So again, just one way to direct water to these planted areas to slow the water down, allow it to infiltrate. This is just simply a list of green infrastructure approaches to managing water. Not all of these approaches will be successful in very arid, dry climates without irrigation. For example, wetlands would not be feasible. However, there is not a one-size-fits-all approach. And many communities tailor their green infrastructure needs to their climate. Sometimes green infrastructure can mean things like planting cactus, desert grasses, and other native drought-tolerant vegetation. The photo on the top here shows what's called a green roof in Salt Lake City, Utah, which is very arid west. So you can see that it's planted some flowers and some grasses. So that's just one example. Here are some of the values or benefits of green infrastructure, as I've mentioned. Obviously, it's used as a water management approach or tool, but it also has climate adaptation advantages or benefits, and it can also have some urban heat island reduction as well. And then more specifically, the benefits include the enhanced groundwater recharge that I mentioned, pollutant reduction, increased carbon sequestration, reduced energy demands. It can provide wildlife habitat and recreational space. One thing that people don't sometimes realize is that it can increase land and property values as well. And it also can be less expensive than gray infrastructure, especially long-term, therefore making communities more water resilient. This picture is at a local university with those permeable pavers I mentioned previously that allow water to infiltrate into the groundwater, therefore reducing or even eliminating any water runoff from this parking lot, depending on the size of the storm. So next I'm going to talk about the economics related to green versus the gray infrastructure, which is your traditional concrete infrastructure. Here are just a few cases I wanted to highlight to demonstrate how green infrastructure can be more cost effective than gray infrastructure. The first case demonstrates how a major city in Denver, Colorado, and their housing authority department used green infrastructure to decrease the cost of their water infrastructure by over half by using what's called bioswales and permeable pavers rather than a traditional water vault. This picture here shows the green infrastructure that they use. So you have the permeable pavers here, you've got bioswales here that they use instead of the traditional water vault, saving over half of their costs. Another case study in Seattle, Washington, where the cost to connect to the city rainwater system was going to be more than 11 Uzbekistani som. However, the cost of designing and building 3 swales, similar to what is shown in this photo, was only 1 billion Uzbekistani som. A significant saving was achieved by not connecting to the city's infrastructure, but rather managing the water on site with these natural-based solutions. So next, I'm going to really focus on green infrastructure in very arid climates. Here is another picture of green infrastructure, which in arid climates can be brown infrastructure. Typically arid climates, we have low precipitation, plentiful sunshine, and very infrequent, but very intense storm events. And the picture here shows a grass roof on this building. Apologize, it's hard to see, but this is in Wyoming, which is located in the arid western United States. And these roofs are very typical and widely used in Norway, actually. And so some more key points on green infrastructure in very dry climates. Sometimes we deal with issues related to what we call prior appropriation, meaning somebody owns that water. As soon as it falls from the sky, it's already owned by somebody. And so that can be a legal challenge sometimes. We also deal with clay soils that can be challenging for infiltration. And therefore the design and engineering for infiltration really for your soil is very important. Irrigation may also be required to get plants and vegetation established. So plant selection is key for the climate you're in. So what are some of the barriers to green infrastructure in arid climates? I think the biggest one would be perceived design, construction, and maintenance costs. There's also usually a lack of connection between different governmental agencies or ministries or departments. There can be a misconception on the economics. And then a lack of integration into regional and site planning is another big one. And then, as always, there's just a lack of trust in new technologies. And again, sometimes we can have irrigation needed to get plants established, which can almost seem counterintuitive. And this bottom picture here, I just wanted to show you, is a parking lot again with permeable pavers right here in red, and these curb cutouts directing or routing the water to this landscaping in this median. And so this is a good photo because it's actually during a rain event, and so you can see how the water is directed into the curb cutout from the permeable pavers that didn't infiltrate the water. And so here are just some more pictures. I thought I'd show plenty of pictures. The left is a alleyway with those permeable pavers again, you can see here. And then the right is a planter box also with these cutouts right here. Kind of see it, that channel the water flow to this vegetated area. And there's also a over drain to prevent any flooding. So we don't want flooding, and so any excess water will be drained to the city. This is a photo from a university also in Wyoming, so very dry climate. This is a green roof, and this green roof is an ongoing experiment testing over 60 native drought-tolerant plants to see their potential for green roofs in our future. So you can see here, sometimes it looks more brown than green, but that's okay because that's what's native for that climate. And so there's a wealth of information and data to support communities switching from green infrastructure and obviously to support water resiliency. So the tools and the information and data out there include design guidelines, maintenance manuals, and technical assistance programs. And so I wanted to circle back to what I mentioned in my opening remarks about drought. Drought resilience and water conservation are something we can no longer avoid. Drought conditions continue to shift outside of historical trends, making forecasting our water quantity and quality more difficult. And so one topic I wanted to just mention was brackish and saltwater can be used to augment water supplies in areas impacted by severe drought. And I would love to learn more if Uzbekistan is using or testing any desalination techniques. And then lastly, I just want to mention one topic. It's slightly outside of water resiliency, but I thought it might be of interest. And it's regarding disinfection byproducts. Disinfection byproducts are formed when disinfectants like chlorine interact with naturally organic material in water used for drinking water supplies, like rivers and canals and lakes. And these disinfection byproducts can also be found in the air when we're doing certain activities like showering or bathing, swimming, dishwashing. And so the most common type of disinfection byproduct is trihalomethanes, and the concentration and type of disinfection byproducts depends on many factors, including where the source water, what is the site, the source water? So the river, the canal, the lake, the water temperature, and the levels of natural organic material or matter in this water, as well as the amount and type of disinfectant used. So why are these important? What we've learned is chronic exposure to disinfection byproducts increases or may increase your risk of cancer, particularly bladder cancer, and other health effects such as reproductive and developmental effects. And so the United States started learning and regulating these compounds, disinfection byproducts, in water supplies in the mid-1990s. And we continue to learn about disinfection byproducts and their negative health impact on human health. So I just wanted to mention that and see if there was any interest in that topic area. And so with that, thank you so much for your time, and I welcome any questions you may have. And I'll turn it over to Elizabeth to moderate any questions.
Thanks so much, Amy. As Amy indicated, we would welcome any questions that folks have. We do have time reserved at the end for more questions and discussion, but any questions you have now are more than welcome.
You may also type your question in the chat box in whichever language you prefer, and the translators, the interpreters will read them out in English to Amy or to Neil. Thank you.
In the event that we don't have any immediate questions, we would encourage folks to continue to think about any questions they might have during the next presentation, and we can circle back at the end. Seeing nothing, I think we can go ahead and proceed with our second presentation for this morning. Neil, would you like to go ahead and share your screen?
Yes, I will do that. Okay, let's launch this. Let's see, I have to switch that again. I lost that toggle for the screen. Oh, that's odd.
Perhaps try resharing.
Okay. Nothing's being cooperative now. Let's see. No, not that. Oh my goodness. Well, there was a simple way to fix this last time. Let's see. Relaunch that and see what we have. Okay.
There we go.
All right. Okay, so thank you all for attending. I appreciate you showing up to hear some of the stories of what we've been doing in the United States in the area of water quality. And specifically, I'm here to talk about groundwater quality and how we've gone about assessing groundwater quality in the United States in the last 30 years at the U.S. Geological Survey. And earlier talks talked about other aspects of the assessments, but today I'm going to talk about how we measured trends in water quality, that is, changes in groundwater concentrations over time. And as part of that, I'll talk about interactions between surface water and groundwater and the long legacy of groundwater that's already contaminated. Then I'll also talk about understanding processes and these processes that help us figure out why the contamination is where it is. And those include what I call master chemical variables, environmental tracers of age, and groundwater flow itself. And I want to emphasize, although I'm talking about groundwater quality today, and most of the chemistries, most of the examples involve chemical processes, a critical aspect is understanding groundwater flow. And as such, the groundwater flow helps us understand where the contamination is And then understanding the distribution of the chemistry often is very helpful at understanding the groundwater flow. So Amy started with a quote, and this was a quote and a cartoon that we had where I worked. And again, I'm in California in the arid West, and this cartoon is hanging on a friend's door. And in the West, whiskey is for drinking and water is for fighting over. Extreme scarcity in many areas. Okay, for those of you that were not able to be at earlier talks, I'm going to take the first 4 slides and do a very fast recap of major points. And I'll begin by reiterating major design principles. First, we were comprehensive in our approach. We collected as much data related to water quality as possible, and also analyzed the samples for as many constituents as possible. So the data included land use, soils, climate, and of course the water chemistry. And it's more efficient to do this up front. It helps you understand the processes. And as far as the sample itself, you can't go back in time. We were consistent in our approach and design, and that's consistent with respect to the design, the implementation, including the field protocols. And this allows us to compare between areas without being concerned that we've introduced biases by using different methods. Finally, the actual sampling approach was for each of the large aquifers that we examined. We broke them up into what we call equal area grids, usually 60, sometimes up to 90 grid cells. They all had the same area, but then within each, we randomly sampled 1 well. And this gives you a spatially unbiased sample. And it also will give you, just based on the number of cells you start with, a rigorously quantified confidence in how large a target, that is how small or large an area of contamination you can detect with that network. The other thing is that we were assessing non-point source pollution, pollution that's widespread in the landscape from diffuse contamination sources such as agricultural activity or urban land use. We were not looking at point sources as one might get from an industrial accident. And then just very quickly, some of the key results from that. The biggest one was that we sampled 25 of the largest aquifers in the nation that are used for both drinking water and irrigation. It constitutes about 70% of the entire groundwater resource in the nation. And the major finding was that the natural geogenic trace elements may affect the health of far more people than man-made chemicals, which is a little counterintuitive because most people are more concerned about the man-made contamination. And we could see this from the chart that shows the distribution. For example, arsenic was found in almost 15% of the wells. The radium was found in almost 8% of the wells. But when we look at the man-made compounds, anthropogenic compounds, they were hardly ever seen, very rarely, in only 2% of the wells, and any one compound was never found in more than 1% of the wells. More specifically, I know there's a lot of agriculture in Uzbekistan, and pesticides are generally not transported in groundwater very easily. And in our most recent study, we looked at 225 pesticides at over 2,700 wells. And we used a very, very precise analytical methods. So we found a lot, 41% of the wells had a pesticide or degradation product, but none of them had a concentration that exceeded a level of concern for human health. So as I said, today, I'd like to talk about groundwater trends. And the question then is, how is the quality of the groundwater changing over time? Is it getting better or is it getting worse? And here's a few basic ideas. First of all, it's important to recall that groundwater moves very slowly, and it's expensive to drill wells and make observations. So first, change might be a better word to use than trends, because trend it implies a direction, increasing or decreasing. But because it's so difficult to measure, it's a little more honest to just describe and quantify the change without really knowing if that's going to be a systematic, consistent trend in one direction. Our approach, the statistical approach, was taken because the change in any one well may not represent what's going on in the larger aquifer. So we sampled 30 wells in what we call a network in one homogeneous land use, one very similar setting, and they were paired. They were designed for a paired statistical test. So we sampled 30 wells, and then we revisited the same 30 wells and sampled them again 10 years later. And statistically, that's much more powerful than if you sampled 30 random wells. So the critical point is revisiting the same wells, although it's very challenging often finding the same wells for a variety of reasons. And then it's also important to understand the well construction and so on, and sample at the same season, because these will also affect the concentration. So this is the example of one such study. The example is taken from the San Joaquin Valley of California. And the small green dots on the map on the left were resampled. In 1986, they had a median nitrate concentration of 2.4, and 9 years later, the median concentration had doubled. It's a very intensively agricultural area, large areas of vineyards, orchards, and vegetable crops, cotton in the south. And the plot at the left, let's see if I can find a pointer here. No pointer. Oh, annotate. Let's try this. Yeah, okay. So the x-axis is the nitrate concentration that we saw in the wells in 1986. And then we plotted the same wells in 1995. So for example, this well had a concentration of only about 7 or 8 milligrams per liter. 9 years later, that well had a concentration of 19 milligrams per liter. So again, that's the power of revisiting the same wells as a group and using a paired sample statistical test. Now that slide did not advance. Let's try again. There we go. Okay, so we've done this at almost 70 places in the country. And this is a website where we're sharing this data. And each of these arrows indicate a change, up and down, and large or small. The black squares are networks that did not change between the sampling. And this, at the left, there's a pull down, so you can examine the change for 16 different constituents, including uranium, arsenic, and nitrate. This map is for chloride, and we can see that chloride is increasing in most of the places in the country that we're evaluating change. So at a much lower level, but we do have a salinity problem, even in the very humid east, especially where we have a lot of snowfall, because we apply road salt to the roads and it runs off and eventually winds up in the aquifers. You can also click on any one of these networks and get additional information, such as the aquifer it's installed in and the depths of wells. So this is the core, this is the focus of our trends assessment and the methodology we're using. There's another approach, though, that we've used to better understand the change at the very small scale and the processes affecting it. And this is what we call space for time. And we've used it to examine trends in agriculture and in some cases in urban areas, and at a very small scale. So this, in this cartoon, this distance may be only a kilometer or two. But we've installed wells along these blue lines, which would be a flow path for the groundwater, where it infiltrates from the surface and then flows through the aquifer to the stream. And then we've used chemical techniques, as I'll describe later, called age tracers. And by sampling this water, we can send it to the lab and determine that it entered the system in 1960 and has moved to this position since then. And we install wells further back, 1980, and then younger water near the water table, 1990. This data was developed a while ago, so it's already quite old, but you get the idea. You can see that the deeper you go and the farther along the flow, the older the water is. So in this case, we also analyzed for nitrates. And on the right, you can see how the nitrate has changed then over the years from about 3 milligrams per liter in the middle of the 1960s to more than 10 milligrams per liter, which is the drinking water limit, by the 1990s. So now you can see why we have traded space for time by analyzing the chemistry of the water. This simply shows an aggregation of the about 20 places in the nation that we've done this. And again, it's very clear that the nitrate is increasing very quickly as we've used much, much more nitrogen fertilizer in agricultural lands. And then that data on that last slide has been converted into probabilities. And for comparison, I've put on the blue text says fertilizer. So, that was not intended. There we go. So this is the nitrogen, the right-hand axis is the billions of kilograms of nitrogen fertilizer used in the United States. So more than an order of magnitude increase in 60 years. Then the red line is from the data I showed you on nitrate in our wells. And you can see that in these agricultural areas, the probability of exceeding the 10 milligram per liter drinking water limit was very low. And then over 60 years, it's increased to 60%. So that's a very important finding. In these very intensive agricultural areas, there's a high likelihood that the water entering the aquifer now has nitrate concentrations above what's permissible for drinking water. So, where's that water going? Well, with the next few slides, I'm going to connect the groundwater system to the surface water system, to rivers and streams. The cartoon at the bottom shows a similar landscape with agriculture at the top. And in 2009, the concentration of nitrate in the stream that was receiving groundwater flow from this region was 3 milligrams per liter. The shallow water under the field had high concentrations of nitrate indicated by red. And most of the groundwater reaching the stream still had relatively low concentrations. When we sampled the stream 10 years later, more of the nitrate had moved closer to the stream, and the concentration in the stream had increased to 5 milligrams per liter. The noteworthy part is this green zone, because what I'm trying to show is that there is a lag time between when you change agricultural management practices and when the chemistry below in the aquifer and to the stream that's receiving water from the groundwater system will change because of the decades-long time it takes to travel to the stream. The same thing will go for a deeper drinking water well. If there was a public water supply here, it would see the slow increase of nitrate moving through the system. And if one reduced the nitrate application, it could still be decades before one would see a change in the deeper well. Oh, this is simply to say that the same thing plays out in much larger landscapes. The map on the right is a map of the area next to Chesapeake Bay. The nation's capital, Washington, is just off to the southwest. Chesapeake Bay is a very important resource, both for fisheries and recreation, and has been impacted by high concentrations of nutrients, both from urban areas and agriculture. The map is colored to show how long it will take groundwater to move from the surface to a nearby stream. The red areas are the tops of the ridges. And from those red areas, it takes roughly 300 years or more for the groundwater. So if you have a cornfield, the chemicals on the cornfield would take 300 years to reach the stream and hence the bay. The green areas in closer proximity to the streams have what we call a residence time of only 3 to 10 years. Unfortunately, people in this watershed have been working for decades to improve the ecological condition of the bay. But what they found is that only about 30% of the tidal waters have attained the standards, the water quality they wish for, and that less than 50% of the monitoring sites on streams, these are non-tidal, are showing improvement. So there's been a lot of work done in this basin, and they understand that it takes a great deal of patience to see change in the system when the contaminants is being moved through the groundwater system. And now this is the exception to that rule. Subsurface drains are installed in agricultural areas to dry out the soil and permit better crop yields and growth. On the other hand, what they do is they intercept shallow groundwater and move it very rapidly to the stream. And consequently, they intercept those very shallow, high concentrations of agricultural chemicals. The example is nitrate here, and the graph shows the nitrate concentration on the y-axis, and the months of the year, the winter, January through July, and the summer, July through September. The upper graph is for the nitrate in the drain water, and you can see it's very high, always greater than 10 milligrams per liter. And the stream receiving this drain water follows that and is also quite high. When the summer gets drier and the drain stops running, the stream chemistry reflects that and the concentrations get very low. So in the central part of the country where we grow lots of maize and soybean, there are a lot of very heavy clay soils, and there are a lot of agricultural subsurface drains. And the interesting consequence is that the deeper groundwater is relatively protected because the shallow high nitrate water is being intercepted and directed directly to the stream. Very briefly, this is not my work, but the agricultural managers in that region have devised systems that they can put in that are passive. They install them, and then the drain water flows through these reactors, bioreactors, and the chemical reactions remove the nitrate through what we call denitrification, microbial action converting it to nitrogen gas. That's expensive. So back to how this lag time plays out, even in the largest watershed in the nation. I'll describe what we found for the Mississippi River Basin. And we had a lot of data here, which is required for the statistics we used. And we'll look at just one site in Missouri, this large watershed. Now, the blue graph, again, is nitrogen input from fertilizer, kilograms per year. If the nitrogen was being carried by runoff to streams, one would expect the streams to go up in the same time period as the fertilizer application. So it went up very steeply here and here. This is the mean annual nitrate concentration in the river, and we can see it's went up very gradually and then steeply. So we did a statistical fit, and it looks like this. So the best fit suggests that because much of the nitrate is reaching the rivers by traveling through the groundwater, and that slow movement through the groundwater system means there is a 7 to 12 year lag between when the fertilizer was put on the land and when it reaches the river. Okay, a bit more chemistry. We're going to talk about the tools that we use for understanding what the major natural and human factors are that influence groundwater quality. And these include both understanding the chemistry and understanding the physics, the groundwater flow. And I talked about these master variables. The geochemical indicators can include major ions, pH, or oxidation reduction potential, which is the electrical charge on the contaminant, which we call redox for short. Environmental tracers that we used include stable isotopes. I won't talk about them today, but I will talk about the age tracers because they're so useful. And these include sulfur hexafluoride, carbon-14, and tritium, which is heavy water. The graph at the right is, you can ignore the detail, but what it is it's a whole group of chemicals that are exclusively man-made. These do not occur in nature. And this is the concentration of these chemicals in rainfall. And the CFCs are refrigerants, chlorofluorocarbons. And you can see how the concentration of these has increased as the use of them has increased in modern society. Well, because these are in the atmosphere, the rain equilibrates with them. When they rain out that year and infiltrate the groundwater system, that groundwater contains those chemistries. So you can analyze that and determine the year of recharge because they're very, very stable. They do not degrade during transport. There's some exceptions, but I'm generalizing here. So that's the tool we're going to use. Redox. So this plot is for one of the networks in California in an agricultural area. And these are household wells. And as I mentioned, the redox, the nitrogen has different redox states. And bacteria will use a variety of chemicals for a food source, including oxygen, including nitrate. So under oxic conditions, we found that most of our wells in oxic conditions had very high nitrate concentrations. But from the wells that had water that had no dissolved oxygen, those are usually deeper or in areas with a lot of organic matter, there's almost no nitrate present. The interesting thing is the green bars show the amount of fertilizer application. The numbers don't matter, but you can see the fertilizer, that is the nitrogen source, is very similar across these categories. So in essence, it means despite a very high amount of nitrogen on the landscape, on the surface, it was not transported to the well in anoxic conditions. Because that chemistry is so important for the transport of contaminants, we've created maps of that chemistry. And then those in turn can be used in other models to explain contaminant distribution. Redox, the oxidation reduction or valence state of the contaminants is important for arsenic, uranium, nitrate. So in this case, we built a model for the glacial aquifer. This is the northern part of the country that was covered by glaciers. It has sands and gravels from the glaciers. And we used a bunch of predictive variables, including the aquifer properties, soil properties, climate, groundwater age. And oh, that's interesting. That touchpad's very sensitive. And this was the result. So it showed us regions that the entire aquifer, this is 20% depth of the aquifer. This map is 80%. And the green is oxic. So in these areas, the chemicals that are mobile under these conditions, like nitrate or uranium, will move down to wells if there's a source at the surface. In the purple areas that are anoxic, these chemicals will not move. But a chemical such as arsenic, which is more mobile under anoxic conditions, may be more of a problem. And in fact, so let's move on to leave the chemistry behind for just a moment, but we're still going to use chemistry because we're going to use the age tracers. And in this case, we're going to look at tracers of age to determine how deep in the aquifer recharge has penetrated since 1950. So how far has water moved from the land surface down into the aquifer in the last 55 years in this study? So we had tracers in, again, a group of wells in the Central Valley of California. Some of the wells had as much as 4 or 5 of these tracers analyzed. And again, they include tritium, carbon-14, sulfur hexafluoride, fluorocarbons, isotopes of helium, and noble gases. And the map at the right is the result. Now, California has a large precipitation gradient. It's much wetter to the north. Again, there are high mountains with snowpack bordering the entire east side, but it's much drier to the south. And as a result, we see that in the north part, the blue areas, water that has rainfall since 1950 has only penetrated 55 meters. A lot of this is because there's less reliance on groundwater pumpage, and there's less agriculture. So the aquifer is not stressed as much. It hasn't penetrated very far. In contrast, in the more arid south, they've pumped a lot of groundwater. The water table has been drawn down, and we can see that water since 1950 has moved as deep as 145 meters into the aquifer. So this is an example, as I said, where the chemistry can tell you a lot about the groundwater movement, the opportunity for groundwater storage, the rate of recharge, important questions for groundwater supply, not just for human health. And finally, you can put these models together. So you can take the output from one model and use it in another model, which we call meta-modeling. And this is just very quickly an example of a meta-model where we took groundwater flow vectors. So you can't see it, but this little diagram was a very detailed groundwater flow model for the whole valley. And we took the vertical velocity vectors from that model for each of its millions of cells and imported that to models of chemistry for the valley. Because if you have a source at the surface, the only way you're going to get it down is having a downward velocity. And the higher the downward velocity, the farther it will penetrate. So we use that to generate models of dissolved oxygen, nitrate, and in this case, arsenic risk as well. So again, this is this interplay between understanding groundwater flow and the chemistry helping you understand the flow. So finally, I did want to show some cases because I've been sharing some really interesting science, but the application is more complicated in real life. So here's some unintended consequences. In the Yakima River in Washington, there was a problem because they used a lot of DDT. The DDT is persistent and attaches to the sediment, and there was a lot of sediment in the river. It's very cloudy. It was bioaccumulating, and the Native Americans that used the fish in the river as a food source were getting too much DDT in their diet. So they implemented best management practices, BMPs, to reduce the sediment and DDT. And it worked. It was very successful. The DDT concentration went down and the river cleared. As you can see in the photo, it's very, very clear water. But when it was turbid from the sediment, there was no vegetative growth. But when the water clarity improved, because they removed the sediment, there was a massive growth of what we call rooted macrophytes, vegetation, aquatic vegetation, because the water was clear and there was still a lot of nutrients. So it greatly improved the DDT problem, created a smaller problem, unanticipated. In the middle of the country, it's dominated by agriculture now. So in some areas, they'd want to restore some of the native grasslands, the prairies. And in one experiment, they took an area and converted it from a maize-soy rotation to a natural grassland landscape. And the ecosystem flourished. The stream draining the area, the concentrations of nitrate went down. But because the wetlands that developed were anoxic, phosphorus was mobilized from the sediments, and the phosphorus in the stream increased. So they were successful at improving the water quality for one chemical, but it mobilized another one. So as I said, there is the very, very complex linked issues. Finally, an example that involved some of my own work in a university in another area. I used some of our data for a study of an aquifer by them where they noted that there was high uranium in irrigated areas of the Western United States. And for their area, they determined that the mechanism for the increase in uranium was that the nitrate from fertilizer was reacting with uranium minerals, uraninite, in the aquifer and releasing the uranium. They also concluded that was true for the entire western part of the country. Unfortunately, there is no uranium mineral, there is no uraninite in the other aquifers, and it's a different mechanism. Uranium is being released by higher bicarbonate from the crop, the root zone respiration, from the irrigated water moving down, and the carbonate complexes. It binds to the uranium on the sediment and liberates it to the water. So sometimes a chemical mechanism is perfectly logical and feasible, but it may not be operating in a different area. So one must be very careful. So finally, key lessons. First, consistent and unbiased sampling is critical to compare among aquifers and to aggregate data from different aquifers. Despite widespread fear of man-made organic chemicals contaminating aquifers, high concentrations were not widespread, but natural trace elements are a widespread problem. Understanding the groundwater flow, you've heard this several times, I think it's very critical. Understanding the groundwater flow system is critical to understanding the spatial distribution of contaminants and change in concentration over time. And of course, as I said, understanding the contaminant distribution tells you about the flow system. The master chemical variables and environmental tracers and age tracers are invaluable for understanding contaminant transport and also how the groundwater flow system works. And finally, the long legacy of groundwater already contaminated means it may be decades before the true efficacy of changes that we implement in agricultural management practice can be known. Thank you. We'd both be very happy to answer any questions.
Thank you so much, Neil, for that presentation. As Neil indicated, we are now opening the floor for questions. As Beth mentioned earlier, please feel free to speak your questions out loud or put them in the chat box in whatever language you're most comfortable in, and the interpreters can provide a translation to English for the benefit of those of us who don't speak Russian or Uzbek. And we would kindly ask before folks ask their questions, if you could say your name and what organization you're with, that would be very helpful.
Добрый день. Меня зовут, значит, Тимур Мавлянов. Я работаю в Узбек-гидрогеологии, унитарном предприятии. Значит, большое спасибо за интересные презентации. У меня есть несколько вопросов. Если можно, значит, я их по очереди задам. Значит, у меня вот первый вопрос вот по поводу как бы значит, по сохранению там влаги в почвах, да, вот создание тротуаров таких пористых, зеленых зон, чтобы больше дождевую воду, значит, хранить для озеленения городских территорий и так далее. А вот есть ли у вас опыт по созданию таких искусственных или природных емкостей подземных для того, чтобы восполнять вот эти грунтовые воды, для сохранения их на более длительный период для использования в дальнейшем? Большое спасибо.
Neil, do you want to take it, or should I take it first stab at it? How would you prefer?
I have no real experience here.
Okay.
Happy for you to.
Okay. So typically when you're doing groundwater infiltration practices with rainwater, it's going to be shallow infiltration. And so typically we're going to be doing, we call them infiltration galleries or basins. And so they're not going to be necessarily deep injection wells or deep, tanks of that nature per se, but it's more going to be very shallow infiltration basins that are really trying to infiltrate into the shallow aquifer. We're not doing deep injection or deep storage, but you can put in storage tanks, underground storage tanks to hold that water for a later time. That is done. It is a practice that is used in very arid climates, but we're not doing necessarily like well injection. It would be shallow, spread it out infiltration basin or gallery is what we call it. And then they could have a tank as well, shallow tank for holding that water for future as well. That is used occasionally. And we would call it an underground storage tank for storing that water. Does that answer your question? I want to make sure I answered it correctly, Eric.
Спасибо. Вот в вашем докладе прозвучало, что вот не имеет значения, какое количество нитратов вносится, да, все равно они достигают подземных вод и загрязняет их на протяжении длительного периода их использования. Вот такой вопрос. При расчете предельно допустимых концентраций, которые как бы оцениваются на влияние не вредные, чтобы для людей было, учитывается ли при разработке ПДК, как они окружают вред или негативное воздействие окружающей среде, именно подземным водам, вот при расчете предельно допустимых концентраций, или только учитывается здоровье человека? Спасибо.
First, I'd like to be clear that especially in the arid areas, many of the aquifers are very oxic and the nitrate is very mobile. It does not get removed. So it is very common for many shallow wells, especially for shallow wells that are used for homes, to be contaminated by nitrate. And there is a lot of concern in the United States for the impact of nitrate and phosphorus on stream ecosystems. So in addition to human health, there is a lot of concern for what we generally would call nutrient enrichment on ecosystems, because it changes them so much. There's been a very large increase, for example, in cyanobacteria blooms in major lakes, and now we've had them in major water supply reservoirs, even in moving water. The Ohio River, extremely large river in the Northeast, had a cyanobacteria bloom a few years ago, and major cities had to turn off their water intakes as the toxins moved downriver. That had not been observed before, and a lot of that is attributed to nutrient enrichment, nitrogen and phosphorus, mostly from agriculture, but also from sewage treatment plants, from wastewater plants. So it is both an environmental, groundwater concern, and surface water, drinking water, and environmental concern. Is there more detail you would like to hear?
Вот у нас в Узбекистане часто связывают загрязнение подземных и поверхностных. Вот с чрезмерным использованием вот нитратного удобрения, скажем, которые, скажем, фермеры или там раньше колхозы употребляли больше, чем положено, да, этих удобрений, чтобы как бы повысить урожайность и так далее. У нас и говорят, что если бы мы соблюдали бы нормы
Yes.
вот, внесения этих удобрений в почву, тогда бы мы таких вот загрязнений не видели. Значит, вы все-таки говорите, что независимо от концентрации вносимых этих удобрений в почву, все равно, да, мы будем отслеживать эти нитраты в подземных водах. Так, да, я понял?
It could be, I would say it could be reduced. And it's very hard. There are just biological limits to how rapidly.
Спасибо, понятно. И вот вот последний вопрос. Вы говорите, что у вас проникает на глубину 55 метров, 145 метров дождевые воды, ну, соответственно, наверное, и загрязнения, да? А вот какой литологический состав этих пород, вот, что они проникают на такую глубину, и за какой период времени? Вот, зависит ли это от ландшафта или от литологического состава пород, которые слагают вот эту толщу, там 100 метров, 140 и так далее? Или это зависит от каких-то сорбционных свойств почв или подвижности этих элементов? Спасибо.
The entire valley is a subsiding trough that's been filling full of sediment for the last 20 to 60 million years. It's a very deep sedimentary basin. It is mostly sands and gravels, but there are clay layers because at times there was no outflow. So there were inland, very large inland lakes, but it's mostly sandy at the surface. So there's very high infiltration rates. As I tried to say, a lot of the difference in the depth results from how much groundwater use there is. In the south end, there's less surface water available, so they pump a lot. So they've drawn down the water table. And the north end, there's not as much agriculture, more surface water, less pumpage. But all of it is unconsolidated sands and gravels.
Здравствуйте, дорогие участники нашего сегодняшнего мероприятия. Я Исабаев Кадыр, гидрогеология. У меня такой вопрос, вы показали какой-то опыт, да, по применению, поменяли где культуру посадки, где кукурузу вы посеяли, и изменилось загрязнение. Это был такой опыт, что вы проверили загрязнение, где это было, поменяли культуру. Это вы специально делаете?
The example I showed was trying to restore cropland to a natural landscape. So it was not going from one crop to another. We have in that map that I showed where we were looking at the change in 68 areas in the country, many of those networks of 30 wells were designed to look at the chemistry below a specific crop. So we do have information on what the recharge chemistry looks like by crop in many corn settings, in some orchards, in some vineyards, in vegetables, because the soils are different and the chemistry, the chemical use, the fertilizer use rate is different. But I don't have experience in changing between crops in the same landscape, though I know that has happened, and it has happened in response to economic, market forces. In California, everyone's planting almond trees right now. The cotton acreage has gone down. There are other areas in the southern United States on heavy soils where they've gone from cotton cultivation to rice cultivation. But honestly, I do not have any data on the change in water chemistry when the crop changes. I'm sorry to say.
Поставлены разные. Я понял, что вы сравнивали участки, посажены разные культуры. Так?
Would you mind potentially repeating that question?
Нет, я имею в
Unfortunately,
виду, значит, я понял так, что вы сравнивали разные участки, где сеются разные сельхозкультуры. Если у вас так, у меня вопрос такой, это, к чему я веду, если там они одинаковые удобрения, если применяют,
Yes.
почему такие разные загрязнители в воде? Может, сама культура это все осваивает, какие-то загрязняющие вещества? Такого анализа у вас было?
We installed wells in private farming areas, so we did not control the fertilizer use rate. We did have data on it, but we did not control it. So the fertilizer rate was different among the crops. I think for example, I think it's about 3 times as much nitrogen on the corn as on the vineyards, on the grapes. But in the corn soy rotation, of course, the soybeans are fixing nitrogen. And in some of the studies, they've shown that following the harvest of the soy, that there can be residual nitrogen moved down into the groundwater as a result of the nitrogen fixation by the soy cultivation. So in some of the models that we've developed, we've had to include the soybean cultivation as a source of nitrate. I don't think it was ever enough to be a large problem with respect to human health, but it was noticeable. But only the legumes, only the nitrogen fixers would do that.
Спасибо, Валь.
Thank you.
Можно вопрос? Батыр Абдуллаев, Институт гидрингио. Мне вопрос такого характера. Первый, вот та, которая миграция нитратов, да? Учли ли именно скорость миграции через породов и горизонтальную миграции тоже? Почему? Потому что та, которая модели уже показана более горизонтальную миграции нитратов. А если учли миграция от породу, тогда какова средняя получена для модела?
Yes, I think it could be confusing because I was using examples from very different landscapes. The cross section with the stream is from a humid landscape. The models that you saw for the Central Valley of California we like to say that it is a vertically dominated system because the natural hydrology has been destroyed. Most of the ground, most of the water entering is irrigation water that gets past the root zone. Most of the water exiting is pumped up wells. So whereas it used to recharge from the mountain front and streams and then flow horizontally to the river and the valley axis, now it basically gets recharged from irrigation and then pumped back up and recharged again. So in different settings in the West, where there's a lot of pumpage and not a lot of recharge, a lot of the movement is very vertical and there's deep penetration. In the East, where it's much more humid and there's more widespread recharge from natural sources, it's a lot shallower and there's a lot more groundwater horizontal flow. But in the glacial area, like in that cross section with a stream and a humid landscape, it may be only a few kilometers and the travel time will, and we've actually modeled the travel time in these different types of aquifers in different climates. And the travel time may be only a few years. Some of these small glacial aquifers are just sand and gravel, a few kilometers, and the entire volume may turn over in a humid climate in a few years. In the Western, in these deep Western basins, some of the water is thousands of years old. And I'm sure that's the case in some of your deep aquifers. So they're very large contrasts around the country, large contrasts in climate and in geology, and hence in movement. Sorry, that was a very long answer.
Спасибо. Спасибо.
Если еще время, можно задать вопрос.
Please.
Извините, меня зовут Расул Бегматов, Узбек гидрогеология. Руковожу мониторингом подземных вод, службой мониторинга подземных вод по республике. У меня первый вопрос связан с докладом Эми Мэбич. Вот скажите, пожалуйста, при каких гидрогеологических условиях и величине атмосферных осадков целесообразно организовать искусственные фильтрации ливневых вод? И второй вопрос. Нил Дубровский касается, по-моему, это, то есть связано с нитратным загрязнением. Вот нитратные загрязнения подземных вод возникают из-за применения азотных удобрений свыше нормы в сельском производстве или же как? В зависимости от, конечно, литологического строения территории и уровня подземных вод. В обоих вопросах можно учесть и литологические строения, и уровни подземных вод. Пожалуйста. Спасибо.
Yes, thank you for your questions. So what we find typically in the US is that kind of this artificial, if you call it, but more kind of going back to natural processes, not mimicking nature for slowing water down and spreading it out and infiltrating it. We find that the need for this is most prevalent in dry climates, very dry, hot climates where you have very limited precipitation. And so where we have a lot of water, so maybe the east side of our country, they have too much water to manage and it's not a problem. Their water supply is not an issue. But where Neil and I live, the very western, mid and western part of the country, it's very hot, it's very dry, and we don't have enough water. And so managing water in these regions and these environments, climates, we found to be the most important. And so that is why it's really, even though it is called green infrastructure, a lot of time it is brown. It is not green because we can't irrigate plants that look very green and beautiful. It may be things that are not very green. It may be brown vegetation and pavers, things that aren't even green at all, not vegetation at all. But natural or artificial created, man-made creations that will infiltrate that groundwater are the most important, where water resources and water supply are the most limited. And that's in climates similar to Uzbekistan. Hot, dry, low precipitation areas. Did I answer that okay? Correct? Or answer the question for what you were asking?
Да, спасибо. И вы не отметили, что при каких литологических строениях и уровне подземных вод это целесообразно, то есть применимо.
Are you talking about shallow, very shallow infiltration from these kind of artificial systems or practices? Or are you talking more kind of, I think, more to Neil, more deep aquifer? I guess a clarification would be helpful.
Но инфильтрация это все равно поступает в первый от поверхностный водоносный горизонт. Поэтому я и спрашиваю, какие уровни подземных вод на этих территориях. Тем более инфильтрируется через литологические строения. Это играет ли роль?
So for what I covered, the kind of more natural based systems, usually your soils are going to be your limiting factor. Clay is going to be a big problem for infiltration. So you're not even getting to those deep rock you're not getting there. If your soil is not conducive to infiltration, that can be a barrier. So we have to take into account the soil more importantly than the underlying rock when looking at infiltration practices from natural-based solutions like I talked about. So you don't even, sometimes you're more worried about the soil conditions than the underlying rock. But Neil, do you want to talk about, kind of from your perspective?
Well, the one perspective I would add is that in many of these areas, there's been significant groundwater depletion. So there is plenty of room for storage of more water in the aquifer. So volume for the recharge is not a problem at all. As Amy said, it would simply be limited by surface permeability. And in areas where the surface permeability is an issue, they'll often install dry wells and to basically bypass the shallow layers, especially in many of these areas have hard pan developed. So there are cities in California that have dry wells all over the city to get the runoff back in the ground. Question about nitrate use and why we have too much in the ground. As I think one of the other questioners noted, very often they use more nitrate than the crop needs. But I think, as I already said, there's a limit to how quickly the crop can take it up. So inevitably, some of the fertilizer will be transported below the root zone and then reach the groundwater. The US government, the Department of Agriculture, has worked very hard at testing and improving fertilizer application. They have a whole education program I'm only partially familiar with. They talk about the R's. It should be the right time of application, should be right form. So they've been developing slow release fertilizers. So especially because a lot of the corn soybean is in humid region. So if you apply the fertilizer and then you have a heavy rain, it will wind up in the stream. So the right place is one of the R's. They often incorporate the fertilizer into the soil to try to keep it from running off if it rains. So again, they're trying to formulate it so it will be released slowly. So they're working very hard at addressing that problem. Is that useful?
Спасибо.
Again, I mentioned the unintended consequences, but traditionally, the first impacts of agriculture, this is humid region mostly, were the very obvious increase in sediment and sediment erosion from the fields during precipitation, and any chemicals, phosphorus in particular, on the sediment were washing into streams. So the earliest, and that led to literally loss of soil fertility, loss of the soil. So the earliest best management practices were implemented to slow down runoff and to retain the water on the field. The problem is, if you retain the water on the field and the ground is permeable enough, your result will be more infiltration of nitrate to the groundwater. So you have a choice. You can have more runoff and more sediment and nutrients in the stream, or you can slow the runoff and wind up with more nitrate going to the groundwater. So it's a difficult balance.
Do we have more questions?
Вот, можно в один вопрос? Вот вы изучаете загрязнение вот, подземных вод кондиционных или некондиционных? В смысле, в дальнейшем эти воды как-то используются? Это первое. И предусматриваются ли у вас какие-то мероприятия по очистке дренажных вод, прежде чем вы их сбрасываете в поверхностный водотой? Спасибо.
Hypothetically, all of that groundwater is potable in the States. There are very few areas where the natural groundwater is too saline to use. There certainly are in the West, but even in yes, but most of the areas, the groundwater is considered suitable for drinking water, with the exception of, again, the naturally occurring trace elements that might require treatment. So basically, in all cases, they're trying to limit contamination because it could be used. The second question was about purifying surface runoff or purifying subsurface drain water. If I could ask a clarifying.
Очистка дренажных вод.
Drainage waters. That one slide I showed is the only thing I'm really familiar with, where they they build a small holding tank in the ground. One of the pits will be filled with a source of organic carbon. It could be just wood chips. And that organic carbon feeds the microbiological activity, and that will create this environment necessary for nitrate to be reduced to nitrogen gas, denitrification. So they are basically small bioreactors, and they run the drain directly into this tank, and then low nitrate water leaves it. And they have a similar system with different filling to remove phosphorus. Those are the only techniques I know where they're actually trying to treat the drain water. They're a little expensive to install. They're passive. The water just flows through under a natural gradient. So there's very little maintenance, and they're effective. Other government scientists from agriculture are looking at taking those drains, and instead of having the single pipe, having the drain water go directly to the stream, having lateral pipes that distribute that flow in the riparian area near the stream, because that zone near the stream, a natural vegetated area near the stream, has a lot of biological activity, and it will remove a lot of the nutrients before it trickles to the stream. So instead of having it go out all at once in a pipe, it's being distributed across that vegetated, what we call buffer, along the stream margin. It's another approach. It's all about slowing it down and providing an opportunity for microbial action to take up or reduce the nitrate.
Большое спасибо. Дело в том, что вопрос возник в связи с тем, что у нас в Узбекистане сотни тысяч гектаров – это засоленные и подтопленные земли. Это вот голодные степи у нас, Приоралье, вот, Каракалпаки и так далее. Поэтому изучение вот этих загрязнений в соленой некондиционной воде, где минерализация дренажных вод достигает свыше 3-7 грамм на литр, конечно, это, ну, изучать там азотное загрязнение, конечно, проблематично. Есть, конечно, территории, где пресные воды мы там изучаем. И уже раз такой вопрос, а изучаете ли вы вот промышленное загрязнение вот, с азотными соединениями, скажем, где-то производство, или у вас таких прецедентов все-таки нет? Вы в основном только на сельскохозяйственное загрязнение обращаете внимание?
We've mainly, early at the beginning of my presentation, I was saying our program looks at non-point sources, distributed sources, and we were not looking at industrial sources, mostly because there are regulations that govern the industrial sources. But yes, there's plenty of contamination from industrial sources. But they're relatively limited in space, and they're governed by regulations. We do have serious problems with salinization in California as well, and in some other Western states. The San Joaquin Valley, in parts of its history, at the southern end, it was a closed basin, so there are some very saline soils. But there still is an outlet to the north. So they spent a lot of time and money installing subsurface drainages and flushing the salts from some of these areas in order to farm. But that's only possible because we had somewhere to dispose of the drain water. You have a very large challenge.
I think we have time for a couple more questions, perhaps. In the meantime, as you can see in the chat, we are requesting for folks to provide email addresses and contact information so that we can send around the recording link and the presentations from today. So please, if you would like to receive those, kindly put your email address in the chat. Are there any other questions?
Один вопрос, не вопрос, предложение есть у нас, Оман Джангиров, Узбекгидрогеология. Вот можно ли на следующих наших совещаниях, вот таких конференциях, если мы какие-то темы назовем, какие-то темы сами назовем, и если возможно будет, вы под эти темы какие-то доклады, если сделали бы, нам бы было бы очень полезно. Спасибо.
Yes, absolutely. I think I speak for both of the experts when I say we would warmly welcome any suggestions, recommendations, guidance you can offer on what topics would be of greatest interest to you and your ministry colleagues. If Neil and Amy are the correct experts, I'm sure they will be happy to present. If they are not the correct experts, as no one is an expert in everything, of course, we will do our best to identify the correct people to connect you with on the US side. certainly.
Большое спасибо. Мы тогда напишем вам наши интересующие вопросы, темы. Большое спасибо.
Yes, absolutely. Please do. I will put my email address in the chat and you can send it to me directly, or you can send it to Beth Gessen at the embassy, who sent out the calendar invite for today, and she can collect the information as well, whichever is easiest. I have just put my email in the chat. Are there any more burning questions for today? And of course, you can also send any follow-up questions, any realizations to the embassy or to myself as well. Our virtual doors are open. All right, hearing.
Большое спасибо вам за сегодняшние очень интересные доклады были, и в прошлый раз были очень интересные доклады. Большое спасибо вам. Мы отошлем вам наши предложения, наши темы. Очень интересно и очень полезно для нас. Большое спасибо вам.
Thank you.
Absolutely. Thank you so much for your participation and for attending these sessions. We had sort of 3 planned, and we are glad to see so much interest and so much engagement. We love the questions. We're very, very appreciative of all of the questions folks have asked. And we look forward to continuing to work with Uzbekistan on these water quality and water resilience related issues. So we look forward to receiving your email. In the meantime, and to just wrap up for today, again, we will be sending out the recording link and the presentations to any folks who wish to have them. We will provide a link to a Google Drive where you'll be able to find all of the presentation documents and the recordings from the previous sessions as well. And we would encourage you to share those with anyone you think would be interested or would want the opportunity to see. We recognize it's early in Uzbekistan and very late here in the United States. For today, want to say thank you to both the experts for their presentations. Also want to say thank you to our interpreters for their amazing job sort of making these sessions happen. And thank you to our colleagues at the US Embassy for organizing this event. We certainly couldn't do it without them. We hope that this will not be the end of our series. We hope to continue to work with you all. We look forward to doing so, and we welcome you to reach out with any and all questions and topics you might want to discuss. Otherwise, I think we will adjourn. We will end the recording and wish everyone a pleasant rest of their day and hope to speak with you again soon.
Thank you.
Thank you all.